Hey everyone, today we're going to be talking about the cell membrane. So if you don't already have your notebook out, you need your notebook out. You can start a brand new page if you want with the heading or the title, the cell membrane. Okay, I know this is a familiar word because we talked about it in cell parts last week. So we're going to dive a little bit deeper into the cell membrane this week. So let me get back to our presentation here. Here are our learning targets. So by the end of this, you should be able to tell me how water and molecules move across the cell membrane. And you should also be able to predict how a cell is going to change when it's placed in a particular solution. All right, nothing to write down on this page, but just a reminder, the cell membrane lets things in and out of the cell. Remember, it's that outer covering of the cell here. It's really actually complex. It's really complicated. You can see this outline of the cell. It actually looks like this up close. So it's not just this like little blanket. It's got all these little tiny molecules that it's made up of. So take a second and think to yourself, what materials might need to get into a cell or out of a cell, right? Because the cell membrane lets things in and out. What might need to get into a cell or out of a cell? So the main thing we're going to be talking about is waste and nutrients. So just like your body, think about your body. What goes into your body? You've got air. Air goes into cells, oxygen, CO2. Nutrients go into cells, right? Just like the food you eat goes into your body. And then what comes out of your body, right? You've got liquid waste that comes out. You've got solid waste. Same thing with a cell, okay? So the cell needs to make sure that it can allow things in and out, and the cell membrane does that. So we're going to look at a little animation here, okay? This animation shows us diffusion. So diffusion is something we're going to talk about with the cell membrane. Let's just take a look at this example, and we don't need to know what diffusion is. We're just going to take a look here. So when I go and I hit play, these molecules are moving. Right? So molecules, you might remember from 8th grade, molecules are always moving. They move really fast in a gas and slower in a liquid and really slow in a solid. And I can change the temperature here, right? But we don't need to worry too much about that. Now I'm going to add a drop of dye. So think of this as like food coloring. So I'm going to click and add a drop. Notice now we've got red dots. What's happening to those red dots? Are they staying in the same place? They're not, right? They're spreading out. So what I want to show you is that anytime, no matter where I click and add this dot of food coloring, eventually they're going to spread out. And what do we end up with? When they spread out, eventually they're going to become kind of evenly distributed. We still have quite a few in this corner. Let's make it go a little faster here. Eventually they're going to be all over here, right? And they're going to be evenly distributed. They're not going to be stuck in this little corner. This idea is called diffusion. So let's go back. Diffusion is the movement of molecules from an area of high concentration to an area of low concentration. So this I need you to write down, okay? This is the first thing you should be writing down after your title. Notice molecules, okay, movement of molecules from high to low. So in order for us to talk about diffusion, notice I use the word concentration. So we got to talk about concentration. Which beaker down here has a greater concentration of molecules? The one on the right. So concentration means stuff, okay? So a greater concentration means it's got more stuff. So what we see in diffusion is that stuff wants to spread out until it's equal, okay? And this is important because it's going to show us how things move in and out of the cell, and we'll get to that in a minute. Here's another example, similar to what we just saw. If we put a drop of food coloring or we put some particles here in this beaker, over time they're going to spread out until they're about equal. If you need more time, just go ahead and pause this if you need more time to write it down. So what do we call it when they're all spread out and they're equal? We call it equilibrium. Okay, so go ahead, write this down. Equilibrium is when concentrations are equal or they're evenly distributed. So no longer do we have stuff just bunched up in one area. It's all kind of what we call uniform. It's all even, it's all spread out really nicely. Stuff likes to be spread out. It doesn't like to be bunched up like this. So more often than not, we're going to see situations where this is happening. It wants to get to equilibrium. So let's show you an example here, okay? You may have seen this before, but if we take a drop of food coloring and we put it into these two beakers, this is an example of diffusion. Now, the only difference between these two beakers is the fact that one of them has warm water and one has cold water, okay? You don't need to know the difference in temperature. You don't need to know anything about temperature, but I'm just telling you the reason they look a little different in the beginning is because they're different temperatures. But notice, in both of them, the red dye is spreading out, right? And eventually that red dye is going to be even. So if I fast forward, even the cold one, it's just going to take longer, but it's going to become evenly distributed. So that dye is going to be in equilibrium, all right? Same thing, we can talk about another example, Axe, right? Body spray, perfume. Anyone ever been in a classroom where one of the guys takes out his cologne or his Axe and sprays it? Why can the people on the other side of the room smell it? Well, because it travels, right? And it wants to spread out. Initially, it's really, really concentrated in that one area where he sprayed it, but then it spreads out, and as it spreads out, it gets to you, which you might be on the other side of the room and you can smell it. So let's take a look at this example, okay? We've got these molecules, right? Whatever kind of molecules they might be. They might be water or oxygen or carbon dioxide. And they're all concentrated right on this left side. What do you think's gonna happen? Remember, what do they wanna try to get to? They wanna try to get to equilibrium, meaning they wanna try to get to equal. So if I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots, how many would you expect to be on either side at the end? 5, right? Now, here's the catch. These molecules don't just like stay here. Remember when we saw in that animation, they're all bouncing around? They're still moving. Molecules never stop moving. So sometimes there might be 6 on one side and 4 on the other, but on average, they're gonna have 5 and 5. So why is diffusion important? Okay, go ahead and write this down. It lets nutrients into a cell and wastes out of a cell. This is how we get things moving in and out of the cell. Again, go ahead and pause if you want more time to write this down. Notice over here, we've got a higher concentration outside the cell. Remember, it wants to get to equal. So where is it going to move? Some of it's going to move inside until it's balanced. This is how stuff moves in and out of a cell. All right, now we're going to talk about something called osmosis. And don't worry, it's a funny word, but it's not that complicated. I want you to take a second and read these two definitions. We already know the diffusion one. Just read them, don't write anything down. So I'll read them to you. Osmosis, movement of water from high concentration to an area of low concentration. Diffusion is movement of molecules from an area of high concentration to an area of low concentration. What's different between the two definitions? Osmosis is with water. Diffusion is with molecules. So molecules could be, molecules are anything that are made of atoms, right? So things on the periodic table. So H2O, water, CO2, carbon dioxide, oxygen, right? They're particles. Osmosis is a molecule, but it's only with water, okay? So it's a special kind of diffusion, all right? So osmosis is with water, diffusion's with everything else, but they're always going from high to low. So I want you to take a second, I want you to pause this slide, and I want you to write down the definition for osmosis. Don't write down the one for diffusion because you already have that in your notes. So let's take a look at another animation here, okay? We're gonna look at osmosis. Notice we've got two different size particles here. We got some small blue ones, we got some big green ones, okay? Now, if I were to make these openings really big, what would happen? Remember, they would want to get to equilibrium. So with equilibrium, we'd have equal on both sides. Okay, so let's see what happens here. So we get some of the blue ones moving on this side, some of the green ones on this side. Notice if I pause it, they're gonna be roughly equal, okay? Right now, yeah, the green ones are over here. That's okay, all right? But some of them are gonna move back, okay? And at any given point, we're gonna have kind of equal concentrations on both sides. But unfortunately, this isn't how the cell membrane works. The cell membrane has really tiny holes. It doesn't let everything through it. So if this is what the cell membrane really looks like, which molecules are going to be able to go through? Just these blue ones. These blue ones are probably like water. Water is really small, okay? So now what we see is the green ones are staying on the left side. The blue ones can still get to equilibrium though, okay? So the cell membrane doesn't let everything through. It only lets some things. Water is one of those things that it can get through really easily, okay? Because water is really, really small. So let's take a look at an example here, okay? Notice I wrote at the top, assume that salt cannot pass through the cell membrane, but water can. I will always tell you what can go through the cell membrane and what can't. You don't have to know that, okay? Water will always go through the cell membrane because it's so tiny. But I'll always tell you if stuff can move through the cell membrane. So we have water is the blue, salt is the red. So we want to look at which way the water molecules will move. So if water is blue, we need to look at where do I have the highest concentration, okay? Now we're assuming this is like a cell, okay? I know it's a really crappy drawing. And that this is like a container or a beaker that's filled with liquid that the cell is in, okay? So let's take a look. Do I have more water inside the cell or outside the cell? I have more inside, right? So remember, it's gonna wanna even out. So it always goes from a high concentration to a low concentration. So here, my arrow, whoops, if I exit out of here, right, I can drag my arrow and show that the water molecules are going to be moving out until they get balanced, okay? Let's do another example. Again, we've got water and salt. Water is blue, salt is red, okay? So it just asks us where the water molecules will move. It doesn't ask about salt, okay? So we just have to look at water. Where is there more water? Is there more water inside the cell or outside the cell? There's more water outside the cell, right? So outside the cell is a high concentration. So it's going to go from high, from where there's a lot to where there's a little, because it wants to get to equilibrium. All right. So again, let me show you, we're going to talk about an example with starch. Remember those big green molecules? Look at how big this molecule is. That's probably not going to fit through the cell membrane. But water, we said, is really tiny. Okay, so water can fit through the cell membrane. So we're going to do an example, okay? And we're going to look at some other examples that have percentages with starch, okay? All right, so here we go. Okay, if you want to copy an example like this in your notebook, it might be helpful to have one of these examples in your notebook. So you can just pause it, draw this rectangle, draw the circle, and then we'll do it together. Okay, so again, I wrote at the top, assume starch cannot pass through the cell membrane, but water can. Okay, so starch can't go through, but water can. And again, I'll always tell you. So we're looking at which way the water is going to move. So where do I have the high concentration of water? Where do I have the biggest number of water? Inside the cell or outside the cell? Inside, right? So water always goes from a high concentration, where I have a lot, to low. So from the big number to the little number. So we would draw an arrow like this. And that arrow is telling us that the water is going to leave that cell, some of it, not all of it, until it reaches a balance, okay? And if you're awesome at math, you might know it's gonna leave it until it's 90 and 90, right? So it's equally balanced. Now our next question says, what will the cell look like? Think about this cell as a water balloon. If water is leaving that water balloon, what's going to happen to the size of the water balloon? It's going to get smaller. So the cell is actually going to get smaller and it gets all like shriveled up. I know that's kind of a terrible picture, but you can just draw like a shriveled up squiggly cell. So instead of being a circle, I'll try to draw a better one. It's just this little shriveled up thing, okay? Let me show you this in real life. Okay, so we're going to check out this video of these cells. These are red blood cells. And they've been placed in this solution. Notice some of them are not very round anymore. They're getting squiggly. Why is that? They're losing water, okay? So they're losing water and they're becoming shriveled up, okay? Even this one's getting shriveled up. So this happens in real life. I'm not just making this up, guys, okay? All right, one more example. Okay, again, if you want to draw this example in your notebook so you have one, I would recommend that, okay? Because I'm sure there's going to be questions like this on a quiz or test, okay? All right, so here, again, we've got to look at what the water is doing. It says assume starch can't pass through the cell membrane, but water can. So starch can't move, okay? If it tries to go through, it's not going to fit. But the water can. So we got to look at which way the water is going to move. So I've got 90% water here, 70%. So remember, it always goes from high, where there's a lot, to low, where there's a little. So we're going to put our arrow here, okay? And remember, if we think about our water balloon, what's our water balloon going to look like if we got water going into it? It's going to get bigger, right? So our cell, and this is a terrible circle, but our cell is going to be really big, okay? So draw a bigger cell. And again, this happens in real life, okay? Let's take a look. So we've got some cells here, and I want you to pay attention. They're getting a little bigger. It's kind of hard to see, but what you're going to see in a second will tell you, look at what happened. They burst open. So cells actually, if they absorb too much water, they will actually burst open, okay? Now, if you're the kind of person that wants to have instructions on how to solve these osmosis problems, if you want these instructions like in your notes, you can write this down, okay? If you're like, nah, Ms. Frankson, I already got it, then don't write them down, okay? But remember, this is what we did. We look at the percent inside and outside of the cell, okay? And actually, I'm going to change this. We looked at the percent water, okay? We drew an arrow from high to low, from the large percent to the small percent. And then we drew what the cell would look like. Remember, we imagined it being a water balloon, okay? So that's it. If you have any questions, let me know, but we're going to be doing a lab shortly, and it's going to talk about a lot of these concepts, okay? So otherwise, have a fabulous rest of your day, and I will talk to you guys all later.